Good afternoon, everyone. Today, this is the fifth week of tutorial session in Chemical Engineering Thermodynamics course by Shashidhar Kumar sir from IIT Tirupati. I'm Namrata Kulkarni, PMRF scholar from IIT Madras. Last weeks, we have studied so many things about the Gibbs energy and free energies, different free energies, and how to calculate the differences in energies in different processes. So when we know the initial state and the final state, everything. Now, this week we are discussing how different different features that state variables, the pressure, volume, temperature, how these three are connected for different substances. We have already talked about ideal gas system. Ideal gas is represented by PV is equal to RT, where we assume that in an ideal gas there are no molecular interactions, and also the molecules are very small, that their volume is not counted when accounting the total volume of the system, and many such things. So these all assumptions are not actually there in real life systems. So this is a graph from Smith and Vanna's textbook, and here we see how the PV plot is there and how different phases of the same substance can exist for different regions. And the same thing, if I'm presenting here, these are isotherms, means different temperatures. At different temperatures, how, if I change the volume, how will the pressure change, and also how pressure will change if I change the volume, okay, and vice versa, like that. So if we see that this is not some PV is equal to RT, like at a given temperature, if I see, for example, T greater than Tc, this Tc means critical temperature. Okay, so if we consider this P into V, if I see the product of the pressure and volume is not constant always. Okay, it is changing with at a given temperature also, it is changing. So when it is constant, that is an ideal gas. But here we can see it has been changing, right? So people have worked on this and come up with different equation of states, right? Different states we say, right? So equation of states, people have worked on that, and now we are going to study different equations of states. So here, as I said, ideal gas assumes negligible molecular interaction, and the real gases cannot be explained using that ideal law. Okay, what we need is some function of P, V, and T. Here we define compressibility factor, that is Z is equal to PV by RT. Actually, this RT by P is V ideal gas. So the comparison between the real volume and the ideal gas volume will give us compressibility factor, which is told by the name itself. So we see in the last graph that this slope, right, is slowly changing. So it will depend, what is the product of pressure and volume will depend on pressure, okay, at a given pressure, the P and V, and at different pressure, the P and V product is different, right? So people have looked into expressing this product as a expansion, as A plus BP plus CP square and so on. And this can be represented like this. And we see that at very less pressures, at very less pressure, the molecules are very far, and we can assume that the molecular interactions are zero in that situation. So then we can say it will show some ideal gas behavior. So we can say that this A is equal to RT and all these terms tend to zero. That's why A is equal to RT. So using that, if we get this here, we'll have Z is equal to 1 plus B prime P and C prime P square and so on. As now we have expressed this product in terms of pressure, it can also be expressed in terms of volume in this format. Okay, and here all these B, C, B prime, small b, small c, all these are dependent on substance and the temperature. Okay, so these are polynomial kind of expression which we can see in this figure. Okay. Many people have worked on expressing these things, finding some equation, fitting into an equation for different states. But real equations are derived based on the statistical mechanics, like what is like the two body interactions inside a gas and three body interactions. All these have been considered to come to tell this uh, virial equations. So these are called virial equations, and these are virial coefficients. Okay. So here the B by V accounts for the interactions between pairs of molecules, that is two body interactions, and the C by V square accounts the three body interaction, which is generally very less common in the gas-like densities. Okay, three body interactions are very rare, but in liquid maybe you can see them. So we can say that here if we see, this is almost like a linear line. And we say, if we find the tangent line near the P tends to 0, that tangent line can explain the behavior to some pressure range. Okay, to some pressure range. That is, this is the tangent line that is equal to 1 plus B prime P. And this can explain the behavior just near till the saturated pressure, and higher than that we need some other equation state. If we see after higher pressures, actually this three body interactions can also be accounted, right? When we see higher the pressure, you're bringing the molecules even more closer. So that's why even this relation you can understand that as the pressure increases, the volume decreases because you're bringing the molecules more and more closer. So that's why the three body interactions become more dominant when it is pressures higher than the saturation pressure. So this BCD curve represents the saturation curve. Okay. Now, so we have this equation, the radial equation, which is explicit in pressure, that is PV by RT, that is called PV by RT, right? And it is cubic in volume because V squared goes to PV cube, like that. Now coming to one of the cubic EQS, this is cubic, right? That's why we are told that it is cubic van der Waals equation. Okay. This can be used to represent both liquid and vapor behavior, and it is expressed as this P into V into RT. So here we can see P plus A by V square I have written and V minus B. Okay, the same expression can be written like this. P is equal to RT by V minus B minus A by V square. So here you can see P is equal to RT something minus there is something. Okay. So this term represents that it is less than what is actually there in ideal gas. So because in ideal gas, we assume no molecular interactions. Okay. So means nothing is pulling, assume some gas is there in a vessel and pressure. How do we explain pressure? Yeah, just a minute. If I have something like a vessel like this or even like this, okay? And whatever is exerted on the wall, that is what you say as pressure. And if some interactions are there, interactions are present, then this pressure is anyway there. The molecules are hitting the wall, but also some very less forces are bringing together also. Okay, so that's why the total pressure becomes P less than P ideal. Okay, that's why we are adding that term to the actual pressure. But this is P ideal when B is also not there. RT by V is P ideal, right? So it's P ideal minus A by V square. So that's why this is P ideal. And why V minus P? So earlier we assumed that some volume this gas has, but we didn't count the volume of the molecules. Molecules also have some volume, right? So that is the D. This is molecules volume, finite size of molecules. So that's how we represent PV is equal to RT, where this is now the ideal. Hmm? So V actual is greater than V ideal and P actual is less than P ideal. And this is the van der Waals equation. Hmm. And this is valid below the critical temperature only. And it has three roots for the volume. Okay, this is a cubic equation. And that's why out of the three roots, the highest to indicates the gas and the lowest for liquid volume. At critical temperature, horizontal inflection at critical point is expected. So as we see here, there is an inflection point and there is no minima or something. Using the same van der Waals equation, if I represent for this T1 less than Tc, it is given like this. Okay, equation. And that's why out of the three roots, the highest to indicates the gas and the lowest for liquid volume. At critical temperature, horizontal inflection at critical point is expected. So as we see here, there is an inflection point and there is no minima or something. Using the same van der Waals equation, if I represent for this T1 less than Tc, it is given like this. Okay, and the same trend is here, but here there is no minimum or maximum, and the same trend is here, but here there is no minimum or maximum. So we were discussing that at this lower temperatures, this minima and maxima are existing. And at the critical temperature, there is an inflection point. And this is what helps us to determine the coefficients there. So consider this real coefficient. And if we see that at this point, rho p by dou v is equal to 0, and rho square p by dou v square is equal to 0. And that's how we will get A and B. So generally, if you solve this, you will get TC, PC, and BC. You can find all these three using this thing. And this is given by the Van der Waals equation. And if you enter this into this, then you can find what are the values of TC, PC, and VC. Now, if you come to any generic cubic equation of state, then this can be represented as this RT by V minus P minus A by V square. Instead of that, you will have V plus epsilon V into V plus sigma P. And here, A is the only thing which is dependent on the temperature. These epsilon and sigma are same for all substances, and they change depending on the method or depending on the particular equation of state. For example, we have different equations, like this is Van der Waals given in 1873. This is a Redlich-Kwong equation. I write down Van der Waals and Redlich-Kwong. This is so Redlich-Kwong. So Redlich-Kwong. And this is Peng-Robinson. So these are named on the work. Okay. And this B and A are given using these TCPC, which are critical temperatures and pressures. And these are only generally readily available. The volume is difficult to measure compared to the pressure, and temperature. So that's why it is all derived in terms of PC and TC. And here there is a term alpha, which is dependent on the reduced temperature. Okay, this reduced temperature is T by Tc. And we also generally have PR, which is T by Tc. So here your alpha is defined in every case, sigma, epsilon, this is omega and psi. And this alpha is an empirical equation here in terms of eccentric factor, omega, small omega, okay? We'll go through some questions, okay? A container has O2 at 5 atmosphere and molar volume of 2 liter per mole. Okay, one thing has to be noted that everywhere we are writing PV is equal to RT. Okay, but generally you might have read everywhere now PV is equal to nRT. So here what we are doing is V by N is molar volume. Okay, this is number of moles, right? So this is molar volume and we are writing every equation state in terms of molar volume. So we want to make it uh, independent of what is the quantity. So this is 2 liters per mole. And if A is equal to this and B is equal to this, what is the temperature of O2? And use van der Waals equation. So now we have P plus A by V square into V minus P equals to RT, right? So I'm writing R equals to T. And R in terms of these, okay, atmosphere and liter. We have the value R is equal to 0.0821 liter atmosphere per mole Kelvin. Okay, and substituting that 5 plus this values, we will get T is equal to 170 Kelvin. Moving forward, which of the following is true for virial equation of state? Virial coefficient are universal constants. No, because these are function of substance and temperature. So these are not at all universal. Okay. Universal constants means something like this R, gas coefficient, Cv minus Cv, is there, right? That. Or G, but that is also varying with the place. All right. These are universal, which don't change. Vital coefficient B represent three body interaction. No, as we have already told, B by B is for two body interaction and C by V square is for three body interaction. Vital coefficient a function of temperature only. So yeah, for a given substance. Yes, provided a particular substance. For some gases, visual equations and ideal gas equations are the same. Mm, See, this is for some gases. No, because we have PV is equal to A plus BP plus CP square and so on, right? So this is RT. This PV is equal to RT is an ideal gas equation when this all terms tends to 0, that is P tends to 0. So it's not like it is possible for all gases, but it is very less pressure. So not for some gases. For some range of pressures, that is very less range, P tends to 0. Virial equations and ideal gas equations are the same. Okay. Boiling temperature is the temperature for which limit P tends to 0. Dou Z by dou P at T is equal to 0. And the boiling temperature. This is at the boiling temperature. What is correct? Okay. So generally what we have, Z is equal to 1 plus P prime P plus C prime P square and so on, right? So dou Z by dou P at constant T equals to, means constant T is taken because the P primes are function of time, temperature only, right? That's why this is P prime plus 2 C prime P plus so on. As P tends to 0, it is equals to only P prime. So at boiling temperature, this is equal to 0. It is given, right? That's why P prime is 0. The second variable coefficient P is 0. This is correct option. The value of compressibility factor at the critical point evaluated using the van der Waals equation of state is what? At the critical point, so what do we have? P is equal to RT by B minus B minus A by V square, right? What do we have? Dou P by dou V is 0 at the critical point, at critical temperature. So minus RT by B minus B square plus 2A by VQ equals to 0. Also, rho square P by dou V square is equal to 0, right? That's why plus 2RT by V minus P whole cube minus 6A by P power 4 equals to 0. So if you substitute this RT by V minus B square from here, then we will get V is equal to 3B. And later, upon substituting, you will get A is equal to, sorry, this is BC, right? Okay. So we'll get later TC is equal to 8A by 27 RP. And upon substituting both of these in this equation, you will get PC equals to PC by 2B minus A by 9B square. So what is the value of compressibility factor? Where compressibility factor is Z is equal to PV by RT. And when you substitute all these PC, VC, and DC in this equation, you will get it as RTC by 2B minus A by 9B square into 3B by RTC equals to 3 by 2 minus A by just a minute. Minus. Okay. This is A by 3B RTC. And here is where you have to insert that A is equal to 27 R square TC square by 64 PC and P is equal to RTC by 8 PC. And you substitute these A is equal to this and B is equal to this and this, then you will get this is 3 by 8 minus 9 by 8 equals to this is 3 by 2 equals to 3 by 8. Using the variable equation, calculate the molar volume and compressibility factor. So P is equal to 473 and P is equal to 10 bar. This is 473. Okay. And material coefficients are given. So what is the V? Now we know that it is a cubic equation here, right? P plus A by B square into B minus B is equal to RT. And so if you can really solve the cubic equation, then it's fine. But generally, we'll be using a calculator, scientific calculator, right? Where you can readily insert the values. Okay. And there will be for V, you should use it at some as a unknown. Okay. This is like a x square. This is x. Okay. Like that you put and solve this equation in the calculator. Then it will ask you for a guess volume. So first, what is being asked here? Molar volume and compressibility factor of isopropanol vapor. So this is vapor here. So out of the three roots, whatever you get, see the three roots can be, one of them is real and two others are complex. And all three are real. And in which one is very less, showing the liquid, and the one is big, large, which is vapor volume. So how can you give the gas volume in this, right? So you need to give different gas volumes and then find out which solution you need to give gas volumes till you find two different solutions. If you're getting complex, then you can be and take only the one real solution for the volume. So if you go for this question, you will be getting two different solutions, and the least one is 3.4 into 10 power minus 3 meter cube, and this is 3.9. Sorry, this is only 3.4. And one is very high, 3.9 into 10 power 7 meter cube. So this much difference is there. So this is what we will consider for paper. And then finally, compressibility factor you can find that is equal to PV by RT. And R you can take in the respective units, this whatever you have taken here. Okay. The R we have is 8.314 into 10 power minus 5 meter cube per mole Kelvin. This is given data. Okay, right? Here, question 6, 1 kilomole. So, N 1000 moles. Yeah. Of CO2 occupies a volume of this much meter cube at this volume 313 temperature. Okay. Compare the pressure given by ideal gas equation. Ideal gas equation is P is equal to RT by, yeah. So nRT by V. Okay. And because this volume is not molar volume, so that's why we have to consider the number of moles also. And Van der Waals equation is given the pressure as P is equal to RT by V minus V minus A by V square. Okay. So using the A, okay, P is equal to nRT by V, I have found P is equal to 68 bar. So I have used this R only, which is 8.314 into 10 power minus 5 meter cube bar per mole Kelvin. Okay, and I'm using the second one. So actually, this is also giving you 68 bar. Okay. One thing to be noticed here is P is equal to R T by V minus B. I have that. Okay. Here R is I am taking bar. So here also you need to change because since this A is in Pascals, so I have converted A into this 10 power minus 5 by V square and completely multiplied by 1000, which will give us 68 power. So since maybe in my calculation, whatever approximation things are there are almost correct. If I take every term differently, then I will be getting somewhat difference, I guess. So both are giving us 68 bar. The last question. The generalized compressibility chart gives the value of compressibility factor as a function of this here, P by PCL, PR, reduced pressure. So, and here we'll have like this set and P, and we will have different different TR, and given the PC is equal to something, you will have a different PR. What is the set? PR and TR. Okay. So like all your equation of states has this PR and TR only mostly. That's why. Okay. So next week we'll discuss regarding the pizza correlations and all for liquids and different phases of substances. So that's all for today. Thank you.